Recall what we just did is that sine and cosine were fine. They are eigenfunctions of the Hamiltonian, of the kinetic energy operator. I'm describing an electron in space by itself, so there's no potential energy. The problem we ran into was that we need a normalization constant. Normalization constant never seems to matter too much in this type of question. It is not equal to a number of times, right? So fail. Okay, so fail, it failed. So what do you do? This is where quantum mechanics is, I'm supposed to tell you that it's, oh, this is so interesting how to do this. No, this is really annoying. That's what it is. It's annoying and sucky. I hate it. I'm not supposed to say that, but it's true. So when you have this situation, we think of eigenfunctions of the Hamiltonian as being special. When you saw s orbitals and p orbitals and d orbitals in freshman chemistry, those are wave functions of the Hamiltonian. We're solving that. You're going to be solving them in this class. They're special. We think of them as being real. So what happens when I have a real solution, but I can't do anything else with them? Because the eigenvalue equation fails. I can't emphasize enough. If this happens, throw it, literally throw it away. It's like the stock of a company that doesn't exist. It is utterly worthless. You don't want it to be, but it is. Just throw it away. This, you do this, just throw it away. It's meaningless. But it can be solved, just not this way. Okay, now I'm going to show you how to do this, and then I'm going to show you why it works. It's going to seem a little funky. Okay, so the way to do this is, okay, now take our operator, which we normally operate on the wave function and get an eigenvalue out, which is not working right now. So instead what you do is you calculate what's called the expectation value. So notice that I've titled this talk expectation value. That is the expectation value. Notice that I've used Maxwell-Boltzmann language. I've described this as an average value. Okay, so what does that mean? The way this works is you're going to have an integral psi star, because remember that the star means complex conjugate because we run into a lot of imaginary things. Here's the operator, and here's the wave function again. Okay, that is the expectation value. Notice that it is almost identical to a Maxwell-Boltzmann question, where you're integrating over all values. And again, that depends on what it is I'm describing in a free wave that's minus infinity to infinity. The reason I'm using sine, cosine, e to the ikx or e to the minus ikx is that this is a particle that can exist anywhere in the universe, left or right. So the correct limits are minus infinity to infinity. You have to know that. Then I'm taking the thing I want the average of times the probability distribution. Remember that the wave function squared, don't forget this is an aside, it's the wave function squared, which by the way, this is the right, one of you asked me if this was the right terminology, it is a probability distribution. It would help if I knew what probability would be. Now remember that because we are in complex conjugate world, complex square root of minus 1i world, that this is a complex conjugate times the wave function. Okay, so you see the complex conjugate times of the wave function times the wave function, which is this, times the thing you want the average value of, integrated over all possible values. It's identical to the Maxwell-Boltzmann, but there is a little funkiness to this. Notice that I have the operator in between them. Right now, I don't quite, actually, I will show you why this works the way it does. I'll show you why this works. Right now, I know it's tempting to just take this and move it over here. You can't do that because often the operator is a derivative. Right, so you can't do that. Anyway, now again, I will explain the underlying mechanism. Why does this work? I will explain that. Let me just do a problem with it first so that it's not, too mind-blowing. I mean, look, it's not, other than the symbology, and hopefully it's not all that hard, right? Now let's see, now what does it do? Actually, what the hell am I saying? I'm going to show you how it works right now, and then we'll do a problem with it. Okay, so let's take another aside. Now remember that often enough, this is the case. So let's do that. Okay, we get an eigenvalue out. Forgetting my x's. Okay, and then this ends up being, since the eigenvalue is a number, we can just draw that out. It's 5 or it's h bar. Okay, and what's this equal to? What's the integral? Oh. What's the integral of the probability distribution over all values? 1. Right, so this is just, right, the eigenvalue. Okay, so it's very simple. Now, there's two things that actually should bother you already. Why do this when I could do this? Right, I use this to solve this. One thing is kind of cool. One thing's kind of cool. I mean, you may have picked that up on the last example. When you're doing eigenvalue equations, you can get stuck trying to untangle the wave function from its eigenvalue. Remember how I was saying, don't simplify, don't simplify, don't simplify. It was because in the end, I needed to make sure that I could separate the eigenvalue from its wave function. You have to be a little careful of that. This just spits out the eigenvalue. It's cleaner. Takes more steps, but it's cleaner. Okay, that's kind of cool. That can really help you sometimes when you have really complicated. It's actually better to do it in a more complicated way when you have a complicated wave function because of the reason I just said. Sometimes when you do the operation, it's hard to see where the eigenvalue is. Okay, number 2 is that this is just this mini justification for what for why, why this works the way it does, but it actually can be applied to our sine problem. Like when I did momentum, let's do momentum, and these will be sine functions. When I apply it to that, I actually can still get the answer out. I can get the correct answer out. And by the way, now remember what I was just saying at the end of last class, for free waves, sines and cosines are free waves that aren't moving. So when I do sines and I make that momentum, I'll get 0. And I'll explain how that works. But before I do that, let me do some concrete examples. Explaining why that works the way it does is going to take a while. Anyway, okay, sorry, I kind of feel like I'm jumping around a little bit, like kind of nuttily here. I'm just Friday, right? So again, this is another way to get eigenvalues out of wave functions. It's another way to do it. It's cleaner. So there's that, which is not bad. It also can be used in problem cases like the one I was just showing you. When I'm trying to get momentum out of a sine, I can't. Actually, you can do it this way and get the correct answer of 0. Now, as for why that works, will be more complicated. And I may get to that today, but I kind of doubt it because I'm going kind of slow. Okay, now let's do one of these. But I want to show you, I want to work through an entire problem from scratch, starting from what's the wave function. And again, we're still doing a lot of free wave this and that, but I want to introduce the particle in the box. More and more, I'll do more particle in the box problems. So here is a potential energy surface. If the electron, which used to be free, is now in a trap, such that to the left of 0, it has infinite energy, to the right of L, it has infinite energy, so it's trapped, then we call it a particle in a box. Okay, I'm certain I can write down the Schrodinger equation for it, however, that won't help me solve it. That's why I want to stop and show you. I want to do all this from scratch. To solve the Schrodinger equation, we almost never use the Schrodinger equation. We look at the problem and just figure it out. Usually we're going to have a bunch of sines and cosines and e, d, I, k, x, and yada, yada, yada. Okay, now, knowing that the wave function has to be 0 here, and 0 here, somebody give me a function that is wavy, yet 0 at 0.
No.
Cosine at 0 is? You are wrong. So, sine. Okay, it's a sine. Hold on, we're going to have a normalization constant. Okay, is that right? Is that right? No, it's not right. Okay, okay, what's k though? Now hold on. Now let's think about what's the first solution we can have. It's going to look like this. Right? So you can give me what k is. You're right, it is kx, but you should be able to figure out what k is. Okay, sine of 0 is 0. Sine, when's the next 0?
Pi over 2.
Pi. It's pi. Pi is half a wave. I always get those confused. I have to Google it every time. Okay, it's pi. Okay, so at x equals L, sine, I better have a sine of pi. How do I do that? Divide by L, and then what? Yeah, there you go. You see my point? You just figure it out. You just figure it out. Sine of pi x over L, when x is 0, I got sine of 0, which is 0. That works. When x is L, I've got sine of pi, which is 0, which works. It has the correct wave. It has a k in it. K is pi over L. It has a momentum, which is the de Broglie wavelength. It's got all the right properties. I think this is correct. But it needs to be normalized. Okay, so again, now you see why I wanted to do this step by step. You can, I'm going to have you do this on homework. I'm going to give you surfaces and say, hey, give me a function. Tell me something that's reasonable for this. You're going to be doing that. Notice that it's not pre-normalized, right? I'm not starting out with the Boltzmann distribution, which has a normalization constant. I have to figure that out on my own. And you need normalization constants when you do expectation values. Anyway, okay, so because you have to have that right when you do it right here. It has to be there. Okay, so let's do this one. Okay, so what I need is so when it's norm, we know that it's going to be, so forget this n, it's going to be sine pi x over L. We know that the normalization constant will be the square root of the integral of sine pi x over L. Okay. Let me stop there and point out to you I've done two things wrong. Help me fix one of them. Does this look right? You've seen this about 3 or 4 times now. Remember that this is about probability. And wave functions are not probability distributions. Square it. Wave function squared. Right, square it. Okay. This is a definite integral. The other thing I'm missing are limits. What are the proper limits?
0 to L.
0 to L. 0 to L. You have that information here. Now the thing is, that actually infinity to minus infinity would actually would work. It's just that the wave function is 0 outside. And so if I didn't, so I have two ways of doing this. Either I could separately integrate minus infinity to 0, where the wave function is 0, but that's 0. And then integrate from L to infinity with 0, but that's 0. Or I can change the limits. Right, so that's why that works the way it does. Okay, so I am now having to solve this. It turns out that, in here, I'm just going to write down the answer. This ends up being, okay, so what I want you to do you remember that I had you integrate sine squared? Do you remember that I had you do that in the homework? And I showed you that. Now, 2 ways to do this. One is to look at the online integrator like Wolfram or Symbolab. You can do that, that's fine. You can also convert it to e to the ikx minus e to the minus ikx over 2i. And I had you do that on a homework. And you can do that as well. Then you apply the limits. So you know how to do that. I'm just going to go ahead and give you the answer because, again, this is a reasonable, easy thing. It ends up being, this ends up being square root of L over 2. Now here's the thing, I want to point out that, again, this is an incredibly, you should have no problem with this. This is really easy, especially because I have no problem with you using an online integrator, or I can give you an identity. Very easy to do this. But now, have I done something wrong? Here's the wave function. Did I do something wrong? All right, so you've integrated it, and you've got square root of L over 2. Well, why didn't, what? Huh? 2 over L. What have I done? Right, it's on the denominator. Right, don't forget that. Here's what you're going to do on tests and homework. I give you a wave function. I say normalize it. You look at the identity or symbol lab or whatever, or yeah, you figure it out, and then you take the wave function and you say square root of L over 2. Wrong. You have to invert it. Right, 1 over that. So don't forget that. Again, forgetting to flip the normalization constant is one of the biggest ways to get this wrong. So look out for that. Okay, next thing. Okay, so now let's do an expectation value. Now that we have this thing, I don't actually, before we do momentum, let's do position. Okay, now remember that the cool thing about expectation values is that they'll work for things that are not the right wave function. When we had the free wave of sine, it's an eigenfunction of energy but not momentum. You can do expectation values to get that. So, and we're going to do that next, but I wanted to take an aside with this because this one's a little bit easier actually. It's a little easier to understand. Okay, now let me point this out to you. I want to get the eigenvalue of position. So if I apply that, now again, I want to point out that expectation values get you out of hard problems that are intractable. Okay, so I'm going to operate with the position operator times the wave function. What's the eigenvalue? Huh? Now remember, the operator x is literally just an x. Huh? Where's the number times the square root of 2 pi sine pi x over 11? Huh? 1. No, x is not 1.
Wait, so we're not taking any derivatives?
No, this is the operator times the wave function.
Doesn't the operator have a caret on top though?
Sure, but it's still the same as an x. Just this x and that sine, pi x, those are the same thing. X is x. Okay, what happens when you have a wave function of energy and you apply a different operator and you don't get an eigenfunction, eigenvalue times the operator? Okay, hold on. Is this happening? Is this operator, here. Okay, so equals, here, trying to use the board rate. So x is the operator, this is the wave function. Are you getting a number times the wave function? Are you getting that?
No.
Of course not. That's ridiculous. X times a function does not return a number times a function. X is x. So what the heck do you do? Well, the answer is you do expectation values. But the bigger picture here is that now you've seen 2 examples of having wave functions of Hamiltonians. This is the wave function of the energy operator. That's the correct wave function of the energy operator. But then I want to know, but then I use a different operator and it's not the right eigenfunction. Again, sine, this is the right wave function for the Hamiltonian operator. It is not necessarily the eigenfunction of other operators. In this case, it is not the eigenfunction of the x operator. So you see, we keep running into this problem. Wave functions for Hamiltonians are not necessarily wave functions of other operators. This is the way out. A question?
Would an operator of X never work?
Okay, so in terms of how could this ever happen, right? It turns out that I will show you in an extra hour how Paul Dirac solved this. So the answer is that this is not the right wave function. So what is the wave function? Have any of you ever heard of the Paul Dirac delta function?
Question. Is that the one where I got a point from meaning everyone else at 0?
Yes, yes. Then you have. Then that's the eigenfunction. Yes. When back in the day, when they started developing quantum mechanics, and they realized that the position operator was just x or y or z, and people realized, wait a minute, there's nothing we can ever multiply by x to get a number times x. That doesn't work. And people thought, oh, quantum mechanics, all this must be wrong, because that'll never work. Paul Dirac came up with the correct function. Multiplied by x does in fact return a number times that function. That is a graduate school level concept, so I'm going to show you in an extra hour how that works. It's kind of fascinating. But it's still the same problem though. Wave function for one operator is not the wave function of a different operator. This is the way out. So let's do that. Knowing that I can't directly apply the operator, what you do, and actually, I mean, you're going to laugh at this at this point. Average value of x is, let's look what I wrote. I said integrate over all possible values. That's 0 to L, because otherwise the wave function is 0. Okay, now the thing about this function is that it's not complex, so that's kind of cool. I've got square root of 2 over L sine pi x over L. The operator is x, which is just an x. I actually, in my notes, I had it simplified. You may notice that it's this is very easy to simplify. Complex conjugate of the wave function times the wave, in wave function. There's no I in it. There's no I in it. So this is nice because the wave function squared is just the wave function squared. Okay, I can take out the 2 over L. I've got the interval from 0 to L. X sine squared pi x over L. Okay, there you go. Now what do? Look in Symbolab, look at the identity, right? So I'm not going to do it. I have it in my notes, but I've blown a lot of time out. Just look it up. Right? These are standard integrals. You can Google it, you can Symbolab it, you can Wolfram website it. And that's fine. Now I hope that you're not so calculus unable that you can't actually solve it, especially because I showed you that trick of turning this into EVIX and all that, which makes it way easy. But just look it up. And what you end up with is L over 2. The whole thing is L over 2. Now, tell me something. Does that look right? Remember my symbology. It's not accidental. The expectation value, notice I used the average value symbol from Maxwell-Boltzmann. Could you answer that just by looking at this? If I said, here's this thing, here's the probability density, what's the average value? You would have gone right in the center, right? Just L over 2. Yeah, makes sense. That's where it is on average. And by the way, it also exposes a little bit of why position operator, you always have to do position operator with expectation value. But it exposes a little bit why that is. Notice that when you're doing operator times wave function, you expect a value times the wave function. Lots of times that'll work, and lots of times it won't. I can tell why it won't work in the position operator. You see, the wave function spans the entire space. It goes, the space of the problem is from 0 to L because the trap makes it from 0 to L. The wave function gives the particle some probability of being between 0 and L. It's true that the maximum probability is about half. It is half. But the wave function says there's some finite probability for being somewhere within 0 to L. So think about this. How could the operator return a single value when it could be anywhere over the space, right? It can be anywhere between 0 to L. So how can the operator return one value when there's multiple values it can have weighted by a certain probability? The answer is it doesn't. It doesn't even make sense to ask that question. The reason that the x operator, that the wave function is not an eigenfunction of the x operator, is because the question is inherently nonsense. You can't say, where is it? Oh, by the way, this thing is somewhere in this room. It has a probability of being somewhere in this room. Tell me where exactly is it in this room? Well, then your response would be, well, you have to give me more information. My response, well, I'm not going to give you more information. I'm going to tell you that there's $1,000 somewhere in this room. It has a certain probability for being anywhere in this room. Tell me exactly where it is. You can't answer that because it's a nonsense question. Right, nonsense question, nonsense answer. Makes sense, right? So then you, again, the solution is expectation values. That's how you get out of these situations. Okay, now, I told you I'm going to tell you a little bit about why does this work. Right? Now, recall that in the derivation of the expectation value, I used the thing I just described doesn't work. And see, this always bothered me about expectation values. In the derivation of why it works, I just used the x times the sine function, which does not return a value times the wave function. It doesn't for position, it doesn't for momentum, does not for momentum in the case of sine and cosine. So how the hell did this really work? This is just a cutesy little proof. This is a cutesy little proof to make you comfortable with it. It's a cutesy little proof to point out to you that it gives you a single number, and again, that's kind of awesome. But how does it really work? Because this proof does not apply to what I just did. How does it really work? Normally, in most classes, you don't actually get taught this, but I can't resist myself and show you how this actually works. And so, unfortunately, this does introduce quite a bit. This is where we're going to have some real nose and eyes bleeding a bit, because I'm going to write something out really longly. Okay, now I'm going to switch back. Particle in the box, forget particle in the box. Let's go back to the free wave. Let's go back to the free wave. Now remember I told you that, let's do p squared over 2m. Let me just pick one or two examples. Okay, there's this one. So I know that e to the ikx is an eigenfunction. It's a good guy. It works with the Hamiltonian. Great. We also know that it's a right chart. It's moving to the right. We know that p squared, and I should be putting little hats on them at this point, sorry. I'm going to forget that every time, so just forget about it. I know that sine is okay with this too. Sine works with this. Better have an x in it. H bar k squared over 2m sine kx. This guy is an eigenfunction of kinetic energy of the Hamiltonian. E to the ikx is an eigenfunction of kinetic energy, the Hamiltonian. But e to the ikx, it's okay with momentum. This one is okay with momentum. This one is not. Junk. Don't even do it. It's junk. It's not even worth analyzing. It's just mathematical noise. It's baby speak. Mathematical baby speak. So what do you do? What do you do? This guy I don't have a problem with. It's a right wave. Even the minus ikx is a left wave. So what about sine and cosine? I'm going to do sine. All right, now here's the trick. Here's the trick. Now again, if you do an expectation value, you're going to get 0. And maybe that's on the homework, actually I forgot, anyway. Plug this into an expectation value, you get 0. That's the right answer. But why does it work? Why does it work? Because that derivation I just gave is actually bogus. Kind of bogus. Here's how. What you do, we're going to do this for sine. For the case of sine, or any situation where we run into the eigenvalue problem, when the eigenfunction does not boomerang back when operated on, what you do is, oh God, I'm sorry, I have to take a little bit of an aside here. Let me get my symbology correct. Let's call the wave function of a Hamiltonian, let's call that psi. Now let's take another operator and multiply it by psi, and this is not true. This is not true. This is the problem we're solving. So what we do have, though, we have functions that do work. They're just not the same. So this is, and this is actually true. I should have actually started with this. So again, we think of the Hamiltonian as special, and that's why wave functions of the Hamiltonian are special. But occasionally we try other operators, and when we don't have an eigenvalue equation, it's a major problem. It turns out there are other functions of that operator that are out eigenvalues. Here's the trick. What you do is you take the guy that you want, and you create a linear combination of the other ones. And there can be multiple ones of these. So it's like a Taylor series, where your expansion is into these other functions. Okay, so that's the idea. Now you see, you couldn't apply that bad operator on this, but you can on that. Because these guys have the right functions. It's, and just in case it's like, well, wait, what the hell is that? Here, you've been doing this the whole time. Sine kx is 1 over 2i. So there's your like weighing factor for making this work. E to the I kx. Your next weighing factor is minus 1 over 2i, e to the minus I kx. And then there's no third or fourth or fifth term. I'm trying to be generic there, right? So here you go. Sine, which is okay with the Hamiltonian, but not with momentum, can be cast into a linear, like a superposition of functions that are okay with the momentum operator. Now I can solve it, right? So there's some weighing factor, which in the case of the right wave is 1 over 2i. There's a weighing factor for the left wave, which is minus 1 over 2i. It's not really all that important. And there you go. Now I can apply the momentum operator on that, and it'll be cool. I can also plug this representation into, what I can do is I can do this again, this way, and show you that it works. Because again, this is kind of bogus. What I did is kind of bogus. I just wanted to show you, I wanted to make it easy at first, but now let me do it for real. Let me do it the right way, which is this expansion way. Expanding, you know, when you go to grad school, you learn some really fancy terms for this. You technically say that you have a complete space of vectors of eigenfunctions, and you can make linear combinations of those functions to span the space of another operator's space. Anyway, you learn all these terms and it goes over your head, and it always means something way, way, way simple. Okay, now there's one thing I want to point out though, that when you've done this right, there are some characteristics of these different functions. One is not too hard to imagine, is that they're normalized. I mean, these are eigenfunctions of another operator, so they still behave themselves. They're still going to be normalized. So this is always going to be true. There's another thing, though, that has to be true. And I'm actually going to prove this. Here, let me just write it down. I hate just writing things in silence, but anyway. Okay. And this is called, there's a word for this. It's called orthonormal. Okay, maybe you've heard that before. Like X, Y, and Z are technically orthonormal vectors. Sometimes eigenfunctions are called vectors as a result of this, by the way. So anyway, normal means that they're still normalized because they're still probability distributions. They're just probability distributions for a different operator. But if I have two solutions, and you've seen this before, either the ikx and either the minus ikx, those are different functions, different eigenfunctions for the same operator, for the same momentum operator. And it turns out that if you multiply them, you're going to integrate to zero. So there's this, anyway. Okay, so now let's do the expectation value momentum. What you end up with is, and I'm going to just do two terms because of like the reason I just did a minute ago. Just like my sign can be done into two terms. And then I have got the operator. And I'm just going to, that's a complex conjugate. Remember, that is the definition. The complex conjugate is there because that's the definition of an expectation value. And the dx or whatever. Anyway. Okay, next step. Now, I'm not able to do anything with this yet, so this thing stays right here. Now, let's operate on this thing. So it's got some eigenvalue. If this is e to the ikx, the eigenvalue is h bar k. So I just want to, the point of that is, don't write that down or anything, it's just that you know what this is. If this is, that's right shark, if this is left shark, then the eigenvalue is minus hk, h bar k. Okay. Next step, where this gets kind of bonkers is that I've got to do a little FOIL thing, right, from middle school. So what I've got is I've got C1 star. Oh, I got the star on the wrong spot, not that it matters. 1 star psi1. Okay, hold on, I gotta go slower. C1 star, C1, omega 1. That star, here we go, there. Sorry, this isn't hard, it's confusing. It's just that there's a bunch of stuff. Okay, I know that there'll be another term. This one I can nail because it's just going to be with a bunch of 2's instead of 1's. So that's not too hard. And hopefully now, from what I just wrote up there, you see that these integrate to the number 1. Now I've got cross terms, and again, I better look at my I gotta actually look at what I'm doing or I'm gonna get lost. Okay, then I've got the inner outer, whichever one it is, C2 star, C1. And I'm just doing this, I'm kind of on automatic right now, so hopefully I'm not screwing this up. And I've forgotten the partials, but anyway. And, okay, I need to end there, and I will. Here. Because this is, we're actually done. I can actually do this in just 2 steps. Okay, px. Here, since I'm done, I'm just going to continue downward. Okay, what's this first one? Okay, what do you think C star C is?
Just one.
It's actually this. And what does the integral turn into? What? Right. Right, wave function squared integrated is 1. Here's the probability distributions. The next one is the same thing with the 2. What about the last two terms?
0.
Right, they're 0 because of this orthonormal probability, which I'm going to prove next time. I don't ever leave you hanging on stuff. I will prove to you that this is true next time. But 0. There you go. That's why it works. You see, what happens is when you decompose a wave function into other functions, the answer is just the wave factor times the eigenvalue of that first one, plus the wave function times the eigenvalue of that second one. So in the case of sine kx, which is e ikx, okay, px, sorry, I'm going way too fast, but px is 1 over 2i, the absolute value of 1 over 2i is 1/4. The expectation value of e to the I kx is h bar k. I know I'm going way fast here, but again, the wave factor is 1 over 2i, so the wave factor squared is 1/4. The eigenvalue of the right shark is h bar k. Now, for left shark, we get the same wave factor. The absolute value of 1 over 2i is 1/4. And its eigenvalue is minus h bar k, because it's moving left. Huh? What's that? 0. That's what you get if you did a cosine. Also 0. Also 0. Okay, I know, and sorry I'm going at the speed of light there. I just want to point out that the reason expectation values work for functions that are not their eigenfunctions is because of this. Because you can turn a wave function into a linear combination of other functions that do work, go through the bloody mess, and this is what you get. So it does work.